Hi everyone, so today we're going to be talking about chords in a circle and all these different crazy relationships that happen in circles. And I gave you note packets to follow along with. So first we're going to talk about two chords that intersect in a circle. So the theorem basically says that if two chords intersect in the interior of a circle, like the red and the green line shown in this picture, then the product of the lengths of the segments of one chord is equal to the products of the lengths of the segment of the other chord. So many words. Basically what that means is that segment A times segment B, so the product of the lengths of the one chord, is equal to segment C times segment D. So that's the formula that we're going to be using. I kind of quickly want to show you why that works. So let's talk about if I drew some auxiliary lines in here. If I connected these chords like this, I am actually creating two triangles. And what you may remember is that these angles are congruent. And then earlier in this chapter, we learned that these angles actually here would be congruent because they actually cut off the exact same chord. Do you see that? See, their endpoints are that chord, and this angle's endpoints are that chord. Okay, so these are forming similar triangles. In chapter maybe 7, chapter 7, we learned that if two triangles were similar, in this case by angle, then their sides were in proportion. So that would tell me then that A over D equals A over D equals C over B. Okay, so that proportion's true. And then the cross products property says then that A times B equals C times D. So that's why this theorem actually works. Let's look at an example. I give you some chords. I have a red chord and a blue chord in this circle, and I tell you that this segment's 10, this is 4, this is A, and this is 8. All I have to do is 10 times 4 equals 8 times A. So we get 40 equals 8A, and so then A equals 5, okay? Can be a little bit harder. I can do 3x and x, and I can do 6 and 8. Now these should all be on your worksheet to follow along with. So that means that 3x times x equals 6 times 8. So 3x squared equals 48. Now we can see that it's a quadratic equation, but there's no linear term, so we're going to divide by 3 on both sides, and that's going to give me x squared equals 16. So because there was no linear term, I'm wanting to use the square root method. I want to isolate the x squared. Now I'm going to take the square root of both sides. So I want you to remember when you do that, you have to have both a positive and a negative 4. When we take the square root of both sides, we will have both a positive and negative 4. But in this case, to solve this circle, our answer, we would get rid of the negative value because we can't have a negative length. So x would be 4. All right, so that's one relationship. There's a lot, so this is going to start to get confusing. I highly recommend you make some flashcards for yourself so that you know these relationships. The next one I'm going to go over is the tangent-secant relationship. The tangent-secant relationship. Oh, and it got cut off. Okay, so the tangent-secant relationship, again, I wrote this out for you in your note packet. When we have a secant and a tangent drawn to a circle, so the red one is a tangent because it touches the circle on the outside. The secant goes through the circle. When we have a tangent and a secant drawn from the exact same point, okay, then the internal and external segments of the secant are equal to the square of the tangent segments. All right, let me show you. So if I call this A, and I call this B, and I call this C, okay? So let's look at this as a formula. That means that A times A plus B. So the external segment times the whole secant is equal to the square of the tangent. So C times C, or C squared. Okay, so again, let's try this. The exterior segment to the whole segment is equal to the square of the tangent segment, okay? All right, we're going to use that formula now, okay? So here we have an example. I know it's not drawn to scale, okay, but I have this segment, exterior segment is 4, this inside is 6, and I have x, and I want to find x. So the theorem says that 4 times 10, got to add them, 4 times 10 equals x squared. All right, again, now I'm left with this quadratic equation, and there's no linear term, so this is a great place to use the square root method. So I'm going to take the square root of both sides. Now I have to simplify, don't I? So I get x equals plus or minus. I look for the largest perfect square that's a factor of 40, which would be 4 and 10. So that would be the square root of 4 times the square root of 10, so it would be plus or minus 2 root 10 equals x. Now remember, we're going to throw out the negative in this case because x we want to be a positive value because it is a segment, okay? All right, I want you guys to try that next example on the page for yourself, okay? And we'll go over that in class. But I want to kick it up a notch, okay? So I'm ready to kick it up a notch. So I've got this circle. And here, I'm actually going to draw in my secant, my tangent. So I got a secant. I have a tangent. There we go. All right. And I don't know, I tell you that this is 4 and this is x. And the tangent's length is 5. All right, so we got to kick that up a notch, don't we? Well, remember, it's the tangent, the square of the tangent segment. So 5 squared is equal to the exterior segment times the whole segment. Now you want to be careful. When you add 4 and 6, it's not 4x, it's 4 plus x, or x plus 4. I'm actually going to write it as x plus 4. All right, so now that's going to give me 25 equals, going to distribute my x, so x squared plus 4x. That's a quadratic equation again, but this time it has a linear term. There's the linear term. So that means I have to get the equation set equal to 0. So I'm going to subtract 25. Okay, so I have 0 equals x squared plus 4x minus 25. All right, and then normally we try to solve by factoring. Is this factorable? Is this factorable? Are there factors of 25 that add to 4, or negative 25 that add to 4? So what in the world are we going to do? Well, back in Algebra 1, you learned that if something wasn't factorable, you could solve by using the quadratic formula. All right, so I'm going to ask you to write down what you remember about the quadratic formula, and we are going to finish this question in class tomorrow because I want to see what you remember, and then we can put everything together for some more challenging problems. All right, guys, have a great day.